All right, so last time we finished the angular momentum. We moved on to a very special topic in this part, the rigid object in equilibrium, lecture 18. Okay, and as I said, in this part, we're not learning any new laws. We're just applying Newton's second law, these two different versions of Newton's second law in a very special a case. When the objects are in equilibrium, they're not moving, they're not rotating. So that means the net force must be zero, net torque must be zero. So you always know how to set up this problem when you see a rigid object in equilibrium. And as I said, the net force equation usually gives you two equations, right? Because you can set it up in x direction, y direction. And the torque equation actually can give you several equations, because if you pick a different pivot, it doesn't have to be a real pivot in the problem. You can pick any point in the problem, you set it up, it's going to be a torque equation. So you do have many equations. You will get many equations out of these two conditions, okay? So now let's take a look at a problem and practice these two laws, okay? Not new laws, but still we want to practice them. So that's the question on slide 2. A uniform beam with the length and mass, okay, attached to a wall by pin connection. Its far end is supported by a cable that makes an angle phi equals 50 degrees, okay, with the beam, okay. A person stands at distance d equals 2 meters from a wall. Apparently the person doesn't have anything to do, okay. Find the tension in the cable and the magnitude of the direction of the force exerted by the wall on the beam. Okay, so let's see. So there are actually three unknowns we're finding. Okay, so let's first draw it out. What is going on? This is a wall here. There's a pivot. The beam is pivoted at the wall. And then there's a cable. Okay, so this is the beam. There's a cable attached to the beam. And then there's also a person standing here. Okay, so the beam is not moving, it's not rotating, right? If this table is cut, actually this is going to fall, the beam is going to rotate, right? So this is a rigid object in equilibrium, so net force must be zero, net torque must be zero. Okay, now let's draw a further diagram. So these two equations, if you want to set up either one, you will need to draw all the forces, right? Even the torque, you need to calculate that using force. So how many forces on the beam? The beam has its own gravity, right? And then the person's gravity is also on it. And then there's a cable attached to the beam, right? The force in the cable, we definitely know the direction. It's always along the cable and away from the object pulling it, right? So intuitively, the force from the cable is going to be in this direction, okay? And then there's also the force from the pivot, right? Remember, it's pivoted at the wall. If this pivot doesn't, the wall and the pivot has a force on the beam, right? So that's why this end is not dropping, it's not moving in that direction. And this force is a little bit tricky. When you see a pivot, okay, you don't assume the force is just along the beam. It's not, okay? A pivot can apply a force on this object, okay, in any direction, okay? So the force of the pivot, like, it's gonna be like pointing in some direction, you don't know. That's why the problem says, find the tension in the cable, find the magnitude and the direction of the force exerted by the wall, which is just a pivot on the beam, okay? If you already know the direction, why does the problem ask you to find the direction, okay? You're not gonna get a stupid problem like that. Oh, it's just along the beam. No. So when you see a pivot, you should be careful. The force from the pivot, you don't know the direction. That direction can be pointing in any direction. You don't know, okay? So that's why the problem asks you to find this direction. In order to specify the direction, I can just say it has an angle theta, right? So I can use the magnitude and angle theta to specify that force, right? The tension, the direction of the tension is always, you always know that because it's always along the cable. So this is going to be 50 degrees. Okay, so these are the 4 forces on this beam. So let's set up these 2 conditions, Newton's second law, still Newton's second law, 2 different versions. The first one, now let's set it up in x and y direction. So you will get 2 equations, right? So that means I'm going to set up net force in x direction and net force in y direction. Okay? So now what are you going to do with this? So you will, so these two forces of gravity, they're already in y direction. Don't need to worry about these 2 guys. You're gonna break them into x and y, right? So the T tension, you're gonna break it into x and y, and we have done that many times when we were studying Newton's second law, right? So this is gonna be Tx. This is going to be Ty. And then the angle is 50 degrees. Okay? So apparently Tx is going to be in that direction. Negative, Ty is positive, right? And then you're going to do the same thing for this force from the wall, this force from the pivot. You're also going to break it into x and y. Then you will have the x component and y component, and then there's an angle theta. Okay, so let's see. So I'm gonna set up these x and y equations. So in x direction, Tx has a component, this Fp has a component. You put them together, Fpx is going to be positive, right? And then tension x direction is going to be negative. And then that's it, right? You only have 2 components in x direction. Put a 0 there. Now, y direction, these 2 guys, they both have a y component up, so positive, right? So Ty positive, Fpy positive, and then minus mg minus big mg equals 0. Okay, so these are the 2 equations from the Newton's second law, the real Newton's second law. Now the torque equation. So I would always set up this force equation first because we're more familiar with forces, right? Then I would set up the torque equation. Now the torque equation, pick a pivot. There is a real pivot in the problem, so why don't we pick this pivot, right? So we're gonna pick this pivot. Pick this pivot, then the torque, net torque equals 0, right? So for each force, you're gonna calculate torque, okay, carefully, using the definition of torque. Torque has a definition, force times arm times sine phi, okay? Now you see that the R is not radius, there's no radius here, right? This R is the arm. So we use the little r for a lot of things, okay? Now, so basically I'm gonna calculate torque from tension, torque from this pivot, torque from the mass, little mg, torque from big mg, and put them together, equals 0. And now let's see, torque from the tension, force, I don't have that, but let's first list all these equations, then we rearrange them, right? Times the arm, what is the definition of arm? From the pivot to where the forces apply. Just draw a line from the pivot to where the forces apply. Don't overcomplicate it, okay? Now, the force is here, the pivot is here. Draw this line, right? So that's going to be the line for the tension. What is the length of this line? That's just going to be the length of the beam, right? Now sine phi angle, in this case it's 50, right? Because the problem already tells you it's 50. And then you should make sure that, because these torques, they may rotate this object in clockwise or counterclockwise, right? And while convention is counterclockwise positive, clockwise negative, there's nothing wrong if you do the other way around. You will still get a 0 on the right. So this guy, think about it. If this is a pivot, the force is in that direction, pulling this end, it's going to rotate this beam counterclockwise. So this is going to be positive. Right. Now the torque from the pivot, this force. So it's going to be this force. What is the arm? From the pivot to where the force is applied, the same point. What is the arm? 0. Okay, so that's going to be 0. I don't need to worry about that. And that's also a conclusion we drew earlier, right? Any force that's through the pivot, you don't even need to calculate torque, because it always gets a 0 arm. It's always going to be 0. Now the torque for these two guys, okay? Torque from little m, force times the arm. So arm, draw a line from the pivot to where the force is applied. This is the pivot. This is going to be the arm for this little mg. What is that distance? That's the little d from the problem. And what is the angle between them? Force is down. This is horizontal, 90 degrees. Okay? So sine 90. Again, is this positive or negative? Think about it. This is a pivot. This force, if this force is pulling this beam down, so the beam is going to rotate clockwise. So this is going to be negative I plug in. Now the last torque, big M. What is the pivot, or what is the arm? You're going to draw another line, right? From here to where the force is applied. So this is going to be the arm. And what is this length? That's going to be half the length of the beam, right? Because the gravity of the beam is right at the center. Again, the angle is sine 90. Is this guy positive or negative? Still negative, because this torque is going to rotate this beam clockwise. Okay, now let's put all these two guys together. This is 0, so I would have TL sine 50, 0. I don't need to care about this. These two guys are going to be negative, so negative mg d sine 90, that's 1, minus big mg 1/2 L sine 90 equals 0. Okay? Now these are our three equations. 1, 2, 3. Okay, so let's see how many unknowns do we have. T is something we need to find, right? We don't know T, but Tx and Ty, you can write them in terms of T, right? So Tx in this, it's going to be T cosine 50 degrees. Ty is going to be T sine 50 degrees. Okay? So you will only have T here and here and here. Okay? And then you also have this Fp x and y. So you can write them as in this expression, in this diagram, you can write them as Fp cosine theta, and this guy equals Fp sine theta, right? Then you will have Fp, one unknown, theta, another unknown, T, another unknown, no, three unknowns in three equations. You can always solve them, right? You just substitute and substitute, okay? But what we usually do is this. Instead of writing the x and y components, so we don't know this guy, we don't know theta angle, instead of writing the xy component in terms of Fp sine cosine theta, we just keep these two unknowns and treat them as the two unknowns, and then I'm just solving for three unknowns. So I'm not solving for instead of solving for f, p, t, and theta, I'm solving for t, fpx, fpy. Why is this going to be easier? Because when you have these three guys, you want to solve them together. These are two forces, this is an angle. So you may have like a sine inverse, cosine inverse, and things like that. The algebra is going to be a little bit harder, okay? But there's nothing wrong if you want to do it that way, okay? Usually people do it this. I'm just solving for three forces, that's easy, okay? And then you see, once you have these two guys, you just use the x and y components. You can go back and do trick to find the net force and the magnitude and the theta angle, okay? So that's what we're going to do here, all right? So I'm going to erase all this, okay? So now we have three equations, but I'm going to replace ty and tx with t and sine and cosine, because I already know the angle. So I would just have one unknown t there, right? So I would just, the first equation becomes fpx minus t cosine 50 degrees equals 0, right? I'm going to keep this x component. I'm going to treat this as one unknown. And the second equation is going to be t sine 50 plus fpy minus, well, you can even combine these two guys, right? So that's the second equation. The third equation is going to be this, TL sine 50 degrees minus mgd minus mg 1/2 L equals 0, okay? All right, so now you're solving these three equations. Three unknowns, three equations. Well, it's going to take you some time to solve it, because you in principle you should substitute and substitute. But this is easier because take a look at the third equation. You can actually solve the third equation for t first, because this equation has nothing to do with the other two unknowns. Right? So in these three equations, you don't have to substitute and then find one equation for y unknown and then solve for that and then go back and go back. You actually solve them independently. Okay? So again, because this is a simplified, well-designed problem for this class. So once you solve for t, then you plug it back into this equation, you get the x component of the force from the wall. You plug t into this equation, you get the force, y component of force. Then you would use the x and y components to find the force and the direction, which is just going to be an angle. Okay? So again, pause the video, do the math yourself. Okay? You're going to learn more if you work with me. All right, so now let's see. I'm going to solve the third equation. If you solve the third equation, you just move these two terms to the right and divide by this, right? So you will get this plus mg divided by L sine 50. Okay, so this number, let me see, what is the number I found? Okay, the D and L, they're already given the problem, right? So, okay, and then at the end, this is going to be 384 newtons. So that's the tension, okay? Then you can go ahead and plug it into the first equation to find the x component, and plug it into the third equation to find the y component, right? So for example, if I plug into the first equation, this is just going to be t cosine 50. Right, plug this number in. This number I found is 247 newtons. And then plug it into the second equation, plug t into the second equation. The y component, it's going to be this minus t sine 50. Right, so this number I found is 588 newtons. Okay, you see, solving for three forces are going to be easier than solving for t force and angle theta, because you're going to have like sine theta and cosine theta, and even you're going to take an inverse. okay? It's just the algebra is harder than solving for 3 forces. Now, this is going to be one of the answers we need. But then the magnitude and direction of the force from the wall, you're going to combine these two guys. So the force from the pivot, which is just the force from the wall, it's just going to be this, x squared, y squared. Right? So this is going to be 637 newtons. So that force is 36. And the angle theta, using this diagram, if you want to use tangent, that's going to be y over x. Okay, so this angle is going to be 67 degrees. Okay, so at the end, the final answer is going to be A. Did you get the right answer? Did you finish the algebra nicely? All right, so this is this question. Okay, so one thing we learned, again, if you see a pivot in the problem, and the problem asks you for the force from the pivot, you don't know the direction of that force, because the pivot is very interesting. It can apply force in any direction. You don't know the direction, okay? So that's why the problem usually, if the problem wants you to find the force, usually we ask even also the direction of the force, okay? So you have 2 unknowns. And then when I set up the torque equation, if there's a real pivot, I would set it up there, right? Use that as pivot. Because when you set it up there, you get rid of this force from the pivot in that equation, right? Because that force, any force through the pivot you pick, always has 0 torque, okay? So that's going to make the torque equation easier, okay? Now let's take a look at another problem, slide 3. Okay, so now I'm going to erase all this. So 2 people are carrying a beam, and then we want to, but they are carrying the beam at different locations and not symmetric, okay? We want to find the force each person exerts on the beam, okay? Don't just divide the gravity of the beam by 2. You're not going to get a stupid problem like that, right? We're still going to use these 2 conditions to solve the problem. So let's first draw it out. Draw the free body diagram of the beam. The beam has its own gravity. Now these 2 people, they're carrying the beam. Of course, they're going to apply a force up, straight up. That's the easiest way, right? So Joe is going to have a force on this beam, straight up. And then Sam is also going to have a force on it straight up. So we are finding these 2 forces. So that means I only need 2 equations actually in this problem. So let's see how we find these 2 equations. First of all, I would always set up the force condition first, because we're more familiar with force. And in this case, you only get 1 equation from the force condition, because there's nothing in x direction, and it's very intuitive, right? Because the force equation, you only need to set it up in y direction, which is just going to be the force from the Sam plus force from Joe minus gravity of the beam equals 0. Okay. Then you need another equation because you have 2 unknowns. Now you're going to set up, so then you have already used force equation, right? Because you can only get 2 from force equation, and the x direction doesn't have anything, so you already used the force equation. Then torque equation, you can actually set up torque equation like at different pivots, so you can actually get multiple force equations from the torque equation. But in this case, we only need 1, so we're just going to use the torque equation once. But in this problem, there's no pivot. So as I said, if there's no pivot, you're free to pick any point as your pivot. right? Because the force, the equation is always true for any point. So you can pick any point as a pivot. You don't even need to pick a special point. A lot of people will say, oh, I'm just going to pick this point. Okay, this looks like a pivot. It's going to rotate this way. No, you don't even need to consider the rotation of this object. In this case, the beam is not rotating anymore. There's no pivot for the beam, right? So you're free to pick any point as a pivot and then just set up the torque equation. For example, yeah, if you like, you can use this as a pivot. You can use the right end as your pivot. You can always use the left end as your pivot, right? Or a better option is this. From the problem we just solved, if there's a pivot and then there's a force through the pivot, then that force is not going to have any value. It's not going to have any torque. So the torque equation is not going to have that force. Okay? So in order to make my torque equation easier, I would always pick a point where there's an unknown force. Okay? So that my torque equation is going to get less unknowns. What do I mean? Let's do this. For example, if I pick this as a pivot, you can pick any point as a pivot. I set up the torque equation. How many torques do I need to calculate? 1, 2, 3. But what is the torque from this force? 0. Right? Because any force through the pivot, it's going to have 0 torque. So when you set up a torque equation, you will have only force of Joule, only have one known in that equation, right? Or you can set up this as a pivot, if you like. If you set up this as a pivot, then how many torques do you need to calculate? 1, 2, 3, okay? This has a torque, this has a torque. What is the torque from this force? 0, because this force is at the pivot I just picked. Okay? So you see that if you pick this as a pivot, you only have one unknown in your torque equation. Okay? So when there's no pivot in this problem, and I need to pick a pivot, I would always pick a pivot where there's an unknown force to make my torque equation easier to solve. But there's nothing wrong if you want to pick a random point and then you have many unknowns in your torque equation. You just still solve all these equations you get. For example, if you pick the center as a pivot, right, how many torques do you need to calculate? 1, 2, 3. But this guy is not going to have any torque. So you will have these two torques in that equation. You would say, well, I don't see any difference. But if you have these two forces in that equation, you have two unknowns in that equation. You can still solve that. You just need to combine this equation with that equation. You solve two equations, you substitute, right? But if I get rid of one of these unknowns, I can just solve this equation first for one number and then substitute that. It's going to make my algebra a little bit easier, okay? So now that's what we want to do. So say I want to get rid of this guy. So let's pick this as the pivot. If I pick this as the pivot, so the torque equation, all right, so torque equation is going to be this. The torque from Sam plus the torque from the gravity plus the torque from a Joule equals 0, but the torque from Joule is going to be 0 because the force is right at the pivot I picked. Okay? Now, how do I calculate these two torques? Use torque, the definition for torque. Torque is always force, arm, sine, phi. Okay? Let's find these two torques. Okay. Now the torque from Sam, the force from Sam, it's unknown. Leave it there. Now the arm from Sam, what is the arm? Draw a line from the pivot to where the forces are applied. Where is your pivot? This is my pivot. This is the pivot I picked. Where the forces applied here. So this, it's gonna be your arm for Sam. What is this value? The problem didn't give you this value. You need to find this value. But you know a lot of numbers, right? You know the total is 76 meters, right? You know this total is 7.6 meters, I'm sorry. And this, you know, this is 1 meter, and this is 2 meters, right? You're gonna use these numbers to find that arm. And then what is this angle? This is the arm, this is the force. What is the angle between them? 90. Okay, is this torque rotating this object clockwise or counterclockwise? First, where's the pivot? This is a pivot, right? If this is a pivot, this force up is going to rotate it clockwise. So this is going to be negative. Now let's do the torque from the gravity. Force is going to be gravity. Arm for gravity. Draw this arm. So this arm is going to be from the pivot, that's the pivot I picked, to the force. So this is going to be the arm for the gravity. Again, you can use these numbers to find that, right? What is the angle? Arm, force, sine 90. Okay? So is this force going to rotate this beam clockwise or counterclockwise? Forget about that guy. This is a pivot. Imagine this beam is fixed here. If you apply a force down, it's going to rotate this whole thing clockwise. So this is positive. Makes sense, right? Because you're going to add these two torques, you get 0. One must be positive, the other one must be negative. Okay? Now let's put them together. This is negative. And then sine 90 is 1. Right? Plus mg are same. Okay, now you see that you don't need to combine these two equations and substitute, right? Because you can just use this equation to find the force from same. Because this equation only has 2 unknown, and then you plug it in, you find the force from Joe. Okay, if you have force Fs and Fj here, then you have to combine them to solve. But again, you just algebra is going to be different. Okay. All right. So again, I want you to pause the video, solve this problem, and then compare your answer with my answer. All right. So let's find out these two arms. Right. So RS. How do you find RS? RS is going to be half of the length minus 1 meter. All right, so that's going to be 2.8 meters, right? Yes, so this is 2.8. Oh, I'm sorry. No. What am I doing? I'm using the wrong pivot. So this is just going to be 7.6 minus 1 meter minus 2 meters. It's going to be 4.6 meters, right? The total length minus this and this, you got this. Okay? And then the arm for gravity, you're going to do half the length minus 2 meters, right? Because you're going to do half the length minus 2 meters. It's going to give you this arm. So that's going to be 1.8 meters. Sorry. Now you plug it in, right? At the end you will find this is just going to be equal to gravity times arm from the mass for the arm divided by the arm for Sam. And then this number it's going to be equal to 1.14 Newton. Okay? And then you just plug it back into this equation. You can find the force from Joe. It's going to be the total gravity of this beam minus force from Sam, right? That's going to be 274.4 newtons. Okay, so the right answer is D. Did you get the right answer? Okay. All right, so this is these questions. So we have already finished this topic rigid object in equilibrium. Okay? Now we're going to move on to the next topic, universal gravitational force. And then, as I said, Newton actually discovered this law when he was working from home. Okay? So let's see who's going to become the next Newton this time. Okay? Newton discovered that there's always an attractive force between any two objects in this universe. Okay? And then the forces, and he also discovered the law to calculate this force. Okay? So, and then I believe like a lot of people know this law. The force equals big G, which is a constant, times m1, m2, the two masses, divided by the distance squared. Now this r is a distance, okay? It's not radius. Sometimes it will become a radius, but this little r is not radius, okay? And it's not always radius. And the big G is a constant in SI units. It's a very small number. Okay? So, and then this is the first time in human history that we discovered force, a fundamental force in nature. So that was a huge discovery. Okay? And then if this is true, why don't we feel attractive force from the things around us? Right? For example, I'm standing in this room, I should feel the gravitational force from any object in this room on me. Right? And then if you are sitting here, then you should feel the force from people around you. But why don't we feel this force? Well, we can calculate this force and see how weak this force is. And then we know why we don't feel this force. So let's use some typical numbers. So slide 5. So let's say I want to calculate the force between two people with the same mass, 50 kilograms. Okay, this is a typical number. And then let's say the distance between them, the r is not radius. A lot of people they tend to say radius when they see a little r. And two people, they don't have radius, right? The distance, let's say, is 50 centimeters, right? 50 centimeters, it's like this. So this is a typical distance when these two people are 50 centimeters apart. So I want you to calculate the gravitational force between them using this equation we just learned. So that's like 8, okay? So pause the video, find this number, and this is just plug and chug. So I hope everyone get the right answer. All right, so if you plug all the numbers in, right, M1, 50 kilograms, M2, 50 kilograms, R, 0.5 meters, converted to SI units. You will find the force between these two people. It's going to be 6.67 times 10 to the negative 7th Newton. Can you feel a force in the order of 10 to the negative 7th Newton? No, you cannot. That's too weak. Right? So that's why we don't feel the forces from things around us in everyday scale, because this big G is too small in SI units, right? It's 10 to the negative 11th. In order to make the force significant, you need to make sure these numbers are big enough, the product of these numbers, right? And distance, you cannot like get too small, too large, one of our. So you have to make like either one of them is big or both of them are big. So that's why we can feel the gravitational force between the Earth on us, because the mass of the Earth is really, really big, right? So that's gonna make this number significant. So that's why we always feel the force from the Earth on us, okay? All right, then what is the connection between this equation, this is a universal equation, and the equation we learned before? We have been using this equation, m times 9.8, to find the force, the gravity from the Earth on us. What's the difference between these two equations? Okay, so that's what we want to figure out next. If this is the universal equation, that means I can also apply this equation between the object and the Earth to find the gravitational force from the Earth on the object, right? If something, this is the Earth, something is on the surface of Earth. So when I use this equation, I use the general equation. Big G, say this guy has a mass, little m, and then the Earth has a big mass of the Earth, okay? I use big M because it's a huge number. Now the distance you use, now you're gonna, because you can't ignore the size of the Earth, so you're gonna use the distance from the center of the Earth to the object. In this case, you see that it becomes the radius of the Earth. So that's why we use a little r down there, because sometimes you will become the radius of something, but it's not always radius, okay? So in this case, if I want to calculate the force from Earth on something on the surface of the Earth, you're just going to do this, right? Now let's do this. Let's just factor out this little m and put everything else together. Why? Because all these three guys, they're constant. Big G is a constant, mass of the Earth is constant, radius of the Earth is constant, okay, the mean radius. Now what I want you to do is this. If I give you the mass of the Earth, slide 8, and the radius of the Earth, calculate this number for you, the number in these parentheses, okay? So just put numbers in, okay? All right? Okay, so this is an easy one, so I hope everyone has done this. If you do this very carefully, this number, you put numbers in, you will get 9.83 Newton divided by kilogram. That's a unit if you put all the units together. Does this number remind you of something? Yes, right? This is the 9.8 we have been using. And this unit, you can show that this is just going to be equal to, this unit is just meters per second square. Newton divided by kilogram, it's just going to be meters per second square. So that means if you use the universal equation, you're always going to calculate if you want to calculate the force from the Earth on anything on the surface of the Earth, you end up always doing m times these three numbers together, m times three numbers together. And then these three numbers are constant, so why don't we just calculate this number and then call it a constant? So I don't need to calculate this every time, right? And then this is 9.8, so we just call this guy little g, okay? So this is just a special form of this equation when you apply this this universal gravitational force equation between Earth and anything on the surface of the Earth, right? You will always get mass times this constant, 9.8. So this is a conclusion from the general equation. This is a special conclusion from that equation. And because this is very useful when we calculate the weight or gravity of anything on the Earth, so that's why we call this also an equation for gravity, right? But this is just a special conclusion from this equation, okay? And then this is going to be true for any planet, right? For any planet, if you want to calculate, so it's not, say it's not Earth, you always get this. Anything, this is not Earth, this is a different planet, okay? I want you to calculate the little g, the gravity from the planet on the mass, you will do this, and then you can still put these three guys together. Why? Because these three guys, they're just going to give me one number, the same number every time. So I can call this guy little g on that planet. So this is going to be a general conclusion, right? So little g on any planet on the surface, it's always going to be this equation. And this is very easy to see, right? So all you need to do is just compare these two equations. These two equations are going to be given on the test. Compare them, you can figure out little g is this, right? You don't need to remember this, and this is not going to be given on the test, okay? If you understand where this little g comes from, you can find out this expression. Okay? So this is the general conclusion for the free fall acceleration on any planet or any star. Okay? So we're going to see some examples next time.